Assalamualaikum. Today, our group will be diving into two interesting topics from MAT 183, which are relative maxima and minima and related rates. Allow me to introduce our members, which are NURSYASYA BATRISYIA, YASMEEN SOFEA, SYAEIRAH, and myself, BATRISYIA. We're ready to present our findings and engage in an insightful discussion. So let's get started and explore these topics with us together. The first topic, relative maxima and minima. In this topic, there are three key elements for you to know, which are saddle point, extremum, maximum, and minimum. Saddle point is a point of a function or surface, which is a critical point but not an extremum. Extremum is the general word for maximum and minimum. Maximum is a high point, while minimum is a low point. There are several steps for you to do to solve questions about this topic. The first step is find the derivative. The second step is let the derivative equal to 0 and find the values of the variables. The third step is you have to do second derivative test. If second derivative more than 0, then it is a minimum value. If second derivative less than 0, then it is a maximum value. For you to understand this topic, we are going to solve one problem statement, which is an open rectangular rattan case with square base is to made from 48 cm square of material. We need to find the dimension of the case that will make the volume maximum and then find the maximum volume.
Now, I am going to show you how to solve the first question. Firstly, sketch a cuboid with H as the height, W as the width, and L as the length. Secondly, we need to find the height of the cuboid. Based on the equation, by adding all the surface area of the cuboid, we get the square base of the cuboid, which is 48. But since we only need to find height, we move all the equation to the other side, except for H. Thirdly, find the volume of the cuboid. The formula for volume is width times height and length. Then substitute H with the equation we just did, and width with the term of L, then simplify the equation. Fourthly, differentiate volume with the terms of L and solve the equation to get the value of L. We use dV over dL. Fifthly, we differentiate the same equation again and put the value of L into the equation to get the maximum volume. And we get -6 as the maximum. And lastly, find the value of H by substituting both value of W and L, which is 4, and we will get H equals to 2. For the second question, we want to find the maximum volume. To solve this, we just have to find the volume of the cuboid where W and L are equals to 4 and H equals to 2. Then we will get the maximum volume equals to 32. Or we can find the maximum volume by using the volume equation from the first question and then enter the value of L. So we get 32 centimeter cube.
Next, we will move on to the related rates. Introduction of related rates. Related rates are rates change associated with two or more related quantities that are changing over time. There are several steps to solving the related rates. First, make a simple sketch if possible. Second, identify what rate you are looking for. Third, set up an equation relating all of the relevant quantities. Fourth, differentiate both sides of the equation in terms of the variable you want. Example, if you want dV over dt, you differentiate in terms of t. Fifth, substitute in values we know. 6. Solve for the remaining rate. This is an example of how to solve related rates. The volume of water in a hemispherical bowl of radius 30 cm is given by V equal to 13 pi x squared minus pi x cubed over 3, where x cm is the depth of the water. If the water was poured in the bowl at a constant rate of 10 cm cubed per second, at what rate is the water level rising? The depth is 8 cm.
Now, I will show you how to solve this question using the steps we mentioned. Firstly, make a sketch of a bowl with radius as 30 and height as x. Secondly, based on the question, the water was poured at constant rate 10 cm per second. So dV over dt is 10, x as 8 because the depth of the bowl is 8. The rate we are looking for dx over dt because we want the rate of rising water. Thirdly, relate all the relevant quantities by first differentiating the volume. Then we get dV over dt equal to 26 pi x minus pi x squared. After that, simplify the equation. Fourthly, put in all the values we know, which are dV over dt is 10 and x is 8. Finally, we solve the equation and get dx over dt as 5 over 72 pi.
Notes for this question. As my friend mentioned before, we need to differentiate the volume. From the equation, there are two parts, which are 13 pi x squared and minus pi x cubed over 3. In the first part, 13 multiplied with 2 and x squared will minus 1, so we're gonna have 26 pi x dx over dt. In the second part, 1 multiplied with 3 and x cubed will minus 1. Then simplify the equation, we're gonna have pi x squared dx over dt.
So, the conclusion is, both related rates and maximum or minimum value problems required a solid understanding of calculus principles, including differentiation and optimization techniques. These concepts provide powerful tools for modeling and analyzing real-world phenomena, from physics and engineering to economics and biology. By mastering these concepts, one gains the ability to describe and predict the behavior of changing systems, as well as find optimal solutions to various problems. These are some references that you can use to further understand both topics.
Thank you for watching our video. Bye-bye!